Hi, my name's Dr. Rebecca Williams, and I'm in the Department of Geography, Geology and Environment. And I'm here to talk to you today about my project on assessing the rock record of hazardous pyroclastic density currents. So interpreting the rock record at volcanoes is the primary way in which volcanologists assess the hazards that the volcano poses to local communities. However, the big problem is the rock record of pyroclastic density currents is incomplete. So when we go into the field, we're only ever looking at tiny portions of the evidence of the eruption that happened that formed those deposits. And what we do is a bit like forensic science, we try and piece all those details together. And some recent research that's been done has shown that some of the bits of evidence that we've been using to identify discrete pyroclastic density currents in the field may actually have only been formed from one pyroclastic density current, but during an eruption that was waxing and waning. So it was getting bigger and then getting smaller and getting bigger and getting smaller. And so what we've realized is that some of the evidence that we've been using in the field to try and reconstruct volcanic eruptions, particularly around the emplacement of ignimbrites and pyroclastic density currents, might not be what we thought it was. So this project is really going to try and tackle that particular question. So we'll have field work where the intention is to investigate the evidence for single versus multiple pyroclastic density currents during major eruptions. We've identified Tenerife as a case study field site and locations in Italy. Tenerife is superb because on the band of still Sur, they've got incredible exposures of ignimbrites. So collecting this kind of data is a particularly good place to do that. But alongside the field work, what we want to do is start trying to tie in process, which is the pyroclastic density current, to the product, which is the ignimbrite. And that's the current big gap in our understanding. So you'll also develop an experimental flume to model how eruption fluctuations might control pyroclastic density current dynamics and how then that is recorded in the artificial deposits that we create in the lab. And then so you'd be able to compare those artificial deposits and our understanding from the lab experiments to what we see in the field, and hopefully we can make some major advances in the way that we interpret ignimbrites in the rock record. So we'll be looking at students who either enjoy fieldwork or enjoy analog modelling. We don't expect particular expertise in either of those because part of your training with this project is to develop that expertise with us, and we'd give you the individual training to do that. So the supervisory team, we can have the next slide, is me. I'm the lead. My research really is around pyroclastic density currents and how we interpret those to better inform hazard assessments. Natasha Dowie, whose research is her PhD research threw up this new question. She's a geologist with expertise in volcanology, particularly around the analysis of uncertainty in modelling. And we've collaborated with Pete Rowley. He's at the University of West England, and he has particular expertise in developing analog experiments. So there's only 2 flumes in the world that can do the experiments that we want to do using aerated currents. Pete's built both of them, and one of them is currently with him at the University of West England. So that's where we'll be doing the experimental work. You'll be joining the Catastrophic Flows Research Cluster, so you'll be joining a small community of people who are already trying to answer questions that are related to this kind of research.